Hi everyone. In today's class,
I am introducing a new topic, heat exchanger. A heat exchanger is a device used to exchange heat between two fluids. They have wide range of applications in chemical and process industries and also used in domestic appliances. In this class, I will introduce the various types of heat exchangers, its fouling and overall heat transfer coefficient. Heat exchangers are broadly classified into two types, direct and indirect contact types. In the direct contact type heat exchangers, the two fluids exchanging heat are coming in direct contact. They have limited applications. But in indirect contact type of heat exchangers, the fluids exchanging heat are not coming in direct contact. Indirect contact type of heat exchangers is further classified into regenerative heat exchangers and recuperative heat exchangers. In regenerative heat exchanger, fluids flow intermittently over the same area and exchange heat. When the hot fluid flows over the packing material used in the flow passage, it retains heat, and later when the cold fluid flows over it, absorbs this heat. High thermal capacity materials are used to store heat in this type of heat exchangers. They have limited applications. In a recuperative heat exchanger, the fluids exchanging heat are separated by a wall. The fluids are flowing simultaneously on either side of the wall. This type of heat exchangers are widely used. Based on the direction of flow of fluid, they may be classified into parallel flow heat exchangers, counter flow heat exchangers, and cross flow heat exchanger. In a parallel flow heat exchanger, the fluids exchanging heat are flowing in the same direction. I have shown a tube-in-tube heat exchanger where hot fluid is flowing in the inner tube and cold fluid is flowing in the angular space between these two tubes. So both the fluids are flowing in the same direction. So when both the fluids flows in the same direction, it is called parallel flow heat exchanger. While flowing through this tube, hot fluid exchange heat with the cold fluid, and both the fluids are flowing in the same direction. In a counterflow heat exchanger, the fluids are flowing in opposite direction while exchanging heat. In this figure, hot fluid is flowing towards right and cold fluid is flowing in the reverse direction. So while flowing through this pipe, it exchanges heat with the cold fluid in the angular space. In a cross-flow heat exchanger, the fluids flows in perpendicular directions. So I have shown a cross-flow heat exchanger where one of the fluid is flowing through these pipes and another fluid is flowing between the gaps of these plates. So the fluid is flowing in this direction and this fluid is flowing in the perpendicular direction. So both the fluids exchanging heat are flowing in perpendicular directions. Again, you can classify this as both fluids unmixed. So this is both the fluids unmixed. In a cross-flow heat exchanger only, this is both fluids unmixed, whereas this is one fluid mixed and other fluid unmixed. The difference is when the fluid flows through these pipes, it is not getting mixed. The fluid flowing in one pipe is not getting mixed with the fluid flowing in the other pipe. So it is not getting a chance to thoroughly mix while it flows. Even in the perpendicular direction, and the fluid flows between the plates, the fluid flowing in this particular gap is not getting mixed with the fluid flowing in the other regions. So while flowing, the fluid is not getting thoroughly mixed. So it is unmixed. Both the fluids are unmixed. But in this case, the fluid flowing in the pipe is unmixed. They are not mixing together. Whereas the fluid flowing between the gaps can flow and mix with the same fluid flowing in the other region. So while flowing, it is getting thoroughly mixed. So this is the difference between these two heat exchangers. In this case, one of the fluid is mixed, the other fluid is unmixed, but in this case, both the fluids are unmixed. The heat exchangers may be classified based on the construction, and based on the construction, they may be classified into tube-in-tube heat exchanger, shell-and-tube heat exchanger, and compact heat exchangers. Tube-in-tube heat exchanger is also called concentric tube heat exchanger. I have shown a figure of a tube tube-in-tube heat exchanger. One of the fluid is flowing in the inside pipe, whereas the other fluid will be flowing in the annular space between the two pipes. So there will be two concentric pipes. Pipe is shown here. This is a pipe. There will be an inner tube, and the another fluid will be flowing in the annular space. The fluid flows either parallelly or in the reverse direction. It may be a parallel flow or a counter flow heat exchanger, but while the fluid flows, heat exchange takes place. So that is called a tube-in-tube heat exchanger or concentric tube heat exchanger. And in a shell and tube heat exchanger, there will be a main shell and a number of tubes will be inside, and fluid flows through the tubes. This is a fluid flowing through the tubes, and it goes out from the shell. On the shell side, the fluid is entering. One of the fluid is entering, and it moves like this because there are baffles provided to move the fluid in the zigzag direction, and on the shell side, the fluid comes out here. So one of the fluid is flowing through the pipes, and another fluid is flowing through the shell. Okay, so this is a shell and tube heat exchanger. This is a sectional view of a shell and tube heat exchanger. And compact heat exchangers, by the name itself, it indicates it's very compact in size, and for getting this smaller size, high area density is required. And for gases, if the area density is 700 meter square per meter cube of volume of the heat exchanger or above, it is classified as compact heat exchanger. And for liquids, surface area, if it is 300 meter square per meter cube of volume or more, it is classified as compact heat exchanger. They have different design, shape, and the sole purpose is to have high heat transfer in a small size of the heat exchanger. So another classification is based on the phase of the fluid while exchanging heat, and they may be classified as condensers and evaporators. So while exchanging heat, these fluids will undergo phase change. Any one of the fluid will be undergoing phase change. In a condenser, while exchanging heat, one of the fluid will condense, and in an evaporator, while exchanging heat, one of the fluid will be changing its phase and evaporating. Now we will see how we can find out the heat transfer in a heat exchanger. While exchanging heat, hot fluid, its temperature will come down, and for hot fluid, the heat is lost, whereas cold fluid, the heat is gained. So we can calculate the heat lost by hot fluid and heat gained by the cold fluid. And in an ideal heat exchanger, the heat lost by hot fluid is equal to the heat gained by the cold fluid, and it's also equal to the heat transfer over the surface while exchanging the heat. Heat is transferring through a separating valve, and the heat flowing through the separating valve is also equal to the heat lost by the hot fluid or heat gained by the cold fluid. So heat lost by hot fluid can be written as mCp into temperature change for the hot fluid. Okay, mCp, this is m is the mass flow rate of hot fluid. So this is a rate of heat lost. In unit time, the amount of heat lost will be getting m is the mass flow rate of hot fluid, and Cp of hot fluid into the temperature change coming for the hot fluid. When the time of inlet, while entering, what is the temperature, and while going out from the heat exchanger, what is the temperature. So temperature change, Thi minus Th0, that will give the temperature change for the hot fluid. So mHCph into Thi minus Th0 will give the heat lost by the hot fluid. And mc is the mass flow rate of cold fluid. mCp into Tc0 minus Tci, temperature of cold fluid at the exit, it will be higher. Cold fluid temperature will be at the exit, cold fluid temperature will be higher, and cold fluid at the inlet it will be less. So the difference between the cold fluid temperatures in the mCp will give the heat gained by the cold fluid. In an ideal heat exchanger, heat lost by hot fluid is equal to heat gained by cold fluid. And this same amount of heat will be crossing the boundary of the heat exchanger. From the hot fluid to the cold fluid, the heat should flow through a separating valve, and this heat transfer through that separating valve, you can write it as UA into delta T. Now, this heat transfer through the heat exchanger is UA into delta T. So, U is the overall heat transfer coefficient and A is the area of heat exchanger, and delta T M, it's a mean temperature difference. Usually the heat transfer you can find out as UA into delta T. When you have a combined mode of heat transfer, generally we specify by your overall heat transfer coefficient U. So overall heat transfer coefficient into area into delta T, that will give the heat transfer. But in this case, I used M subscript, that indicating the mean temperature difference. Since the temperature difference is not constant, in the inlet of a parallel flow heat exchanger, both the fluids are entering, and the hot fluid will be at a higher temperature and cold fluid will be at a lower temperature, and more amount of heat flows this time. So temperature difference is more. When you come to the end of the heat exchanger, the hot fluid temperature has come down and cold fluid temperature has gone up, and the temperature difference will reduce. So this temperature difference along the length of the heat exchanger is not constant. So the temperature difference is continuously changing along the length of the heat exchanger. So we need to find out a mean temperature difference or average temperature difference. Just a mere average will not work out here, since the temperature variation is not linear. So we need to find out a mean temperature difference, and if you get the mean temperature difference for the heat exchanger, you can find out the heat transfer as UA into delta Tm. So this also will give the heat transfer through the heat exchanger. So you can find out the heat transfer in a heat exchanger, either heat lost by hot fluid or heat gained by cold fluid, or the heat crossing the boundary of the heat exchanger. Now we will see what is fouling of a heat exchanger. After an extended period of time, the heat exchanger may get corroded, or sediments may deposit on inside the or outside the tubes, and any other kind of deposits may change the overall resistance of the tube walls. And this will increase the resistance to heat transfer. Maybe fouling can take place inside the tubes or outside the tubes. So based on which side the fouling happens, we can add a fouling resistance while calculating the overall resistance of the heat exchanger. So you will have a fouling resistance on inside if heat exchanger tubes are getting fouled from inside, or you may add a fouling resistance on outside, or both sides. If a fouling takes place, we add the fouling resistance inside and as well as outside. So fouling is a process of a heat exchanger. After an extended period of use, its tubes may get corroded, or scales or sediments may get deposited inside or outside or both sides of the tubes, and this is known as fouling. The result of fouling is to increase the overall resistance of the heat exchanger. Overall heat transfer coefficient. We already studied overall heat transfer coefficient, especially when you have a combined mode of heat transfer. It's the easiest way to represent the heat transfer by a simplified equation. Q is equal to UA into delta T, where U is the overall heat transfer coefficient. So generally, we in this heat exchanger we have two fluids. So I have shown the concentric tube heat exchanger. Here this is inside tube and this is an annular space. So heat flows from inside to outside. Assuming that hot fluid is inside, heat flows from inside tube to the outside. So this heat flow is by convection from inside. Initially it is from fluid to surface is by convection, and through the wall, the heat exchanger wall, heat is crossing by conduction, and from the outer surface heat is flowing by convection. So heat is initially flowing by convection, then flowing by conduction, and then again flowing by convection. So this is a combined mode of heat transfer, and the easiest way to represent this heat flow is by overall heat transfer coefficient U. So you can get the heat transfer, heat flowing through this wall as Q is equal to UA into delta T. Where delta T I already mentioned, the delta T, because the temperature difference here existing on one side and other end of the heat exchanger will be different. Here you will have one temperature difference, and other end you will have a different temperature difference. So along the length of the heat exchanger, the temperature difference between the hot and cold fluid is changing. So here you have one temperature difference, other end you have different temperature difference. So the temperature difference is not constant along the length of the heat exchanger. So you have to find out an average or mean value of temperature difference. So you can find out the total heat transfer as Q is equal to UA into delta Tm, where A is the heat exchanger area, that is the area of the heat exchanger. You may take inside area or outside area. When you take inside area, based on the inside area, you have to calculate U. So the overall heat transfer coefficient you can calculate based on inside area or based on outside area. And we know that 1 by U is given by AR. 1 by U is equal to AR. Now if you take inside area, it is UI. So inside area, for inside area, overall heat transfer coefficient is based on inside area. To represent that, you use UI. So in case of a composite wall, when you calculate the overall heat transfer coefficient, it is area is constant. Area of a plain wall is constant. So there is no difference. But in this case, the area is continuously changing. From inside you have one area and outside you have a different area. So area of heat flow is also changing while the heat flows through this cylinder wall. So since area is changing, you need to specify the area based on which area you are calculating the heat transfer coefficient. So if you are calculating based on inside area, that is UI, and if you are calculating based on outside area, it is U0. So you can write this 1 by UI is equal to AI into R, AI into overall resistance. Overall resistance, you have resistance to the flow in the flow path, you have convection resistance. First one is convection resistance. Convection resistance, you know, 1 by AH. 1 by AH. But here, inside area and inside heat transfer coefficient. For convection from inside, let us take that as HI. So 1 by AI, HI is the inside convection resistance. Then RFI by AI is the fouling resistance. This is the resistance to fouling inside. So this is a fouling factor. We call it as fouling factor for inside surface. Divided by AI. RFI is fouling resistance for unit area. You have to divide by AI to get for the total area. More area, the resistance will decrease. So you have to divide by the resistance to get the resistance for the entire inside area. This RFI is for resistance for unit area, and then divide by total area, inside area, that will give the total fouling resistance. So RFI by A is total fouling resistance. Then you have conduction resistance. Conduction resistance through the wall. 1 by 2 pi KL, where K is the thermal conductivity of the material of this wall, and L is the length of the heat exchanger, into log R0 by Ri. R0 is outside radius of this inner pipe, and Ri is the inside radius of the inner pipe. So you get the conduction resistance. And again, you may have a fouling factor on outside. If a fouling is there, you can add this factor. Similarly, inside, if fouling is taking place, then you can add this factor. So fouling factor is Rf0 divided by A0 will give the total fouling resistance. This is for unit area. Fouling factor is for unit area. What is the resistance for unit area? Divided by area will give the for the total area plus convection resistance from outside 1 by A0 H0. So this inside bracket is the total resistance to heat flow into AI will give the 1 by UI. So if you take AI inside, you will get 1 by HI plus AI is multiplied, you get RFI plus AI is what is inside area? Inside area of a cylinder is 2 pi Ri is the circumference into length. So 2 pi RIL is the inside area. So 2 pi, if you take A inside, 2 pi RIL. So 2 pi L cancels, you get Ri by K. Ri by K is, Ri is di by 2. So you get dA by 2k. So when you take A inside, A is 2 pi RIL, 2 pi L cancels, Ri by k, Ri by k is dI by 2k into log R0 by Ri, R0 by Ri, whether it's a radius ratio or diameter ratio, it's same. So R0 is D0 by 2, Ri is dI by 2, the 2 cancels, you get D0 by dI. And when you take AI inside, AI by A0 is AI is 2 pi RIL and A0 is 2 pi R0 L. So 2 pi L cancels, you get Ri by R0 or dI by D0. Ri by R0 is dI by D0. So area ratio in case of a cylinder is equal to diameter ratio. So you can replace area ratio by diameter ratio. Plus you get AI by A0. AI by A0, once again area ratio you can replace by diameter ratio. AI by A0 you can write it as dI by D0. So this is the equation for overall heat transfer coefficient based on the inside area. So 1 by UA you will get as 1 by HI plus RFI plus dI by 2K log D0 by dI plus RF0 dI into dI by D0 plus 1 by H0 dI by D0. If you know fouling, these two terms will vanish, and if the thermal conductivity of material of this pipe is high and the thickness is very small, thickness of the wall is small, that is D0 by dI tends to 1, this term also vanishes, and you will get 1 by Hi plus 1 by H0 into dI by D0, ratio tends to 1, you get 1 by Hi plus 1 by H0 as the overall heat transfer. Then there will not be any differentiation between UA and U0 also. You can represent 1 by U is equal to 1 by Hi plus 1 by H0. There will not be much difference between UA and U0 because area difference will not be much if the thickness of the separating wall between the fluids decreases, and if the thickness is very small, AI by A0 ratio will tends to 1, and DI and D0 the difference will become very small. Now let us calculate the heat transfer coefficient based on the outside area. So this is a calculation for heat transfer coefficient based on the outside area. 1 by U0 is equal to A0 into R. So overall resistance is same. Instead of AI, you need to multiply with A0. So if you multiply by A0, A0 by A0 area ratio is diameter ratio. So you get 1 by HI into D0 by DI. And here, when you multiply with A0, 2 pi R0 L, 2 pi L cancels, R0 by K, R0 is D0 by 2, so you get D0 by 2K, and you log R0 by Ri, plus RF0 by A0, because RF0 by A0 when you multiply, you get RF0, so A0 you are multiplying, you get RF0, and again when you multiply with A0, you get 1 by H0. So you get 1 by U0 is equal to 1 by Hi into D0 by dI plus RFI into D0 by dI plus D0 by 2K into log D0 by dI plus RF0 plus 1 by H0. Now if the thickness of the wall is negligible or not stated in the problem and no fouling, U is given by 1 by U is equal to 1 by Hi plus 1 by H0.